Thank you. It's a pleasure to speak here today. Thanks to the members of the organizing committee. After seeing the most sophisticated blackboard I've ever seen in action, I'm tempted just to play with it during my lecture. So I'm going to talk about hybrid solutions of family of elliptic equations. And let me begin by giving you some background. There are many problems that arise in Hamiltonian systems or in partial differential equations that have certain common features. In particular, the equations are defined on an unbounded domain, say R in the temporal case or Rn in the spatial case. So it's an unbounded domain. Secondly, there's some symmetries in the equations. So if U is a solution, then so is, say, U of x plus Zn. That's in the Rn case. So you can shift solutions in this fashion, and you'll also get another solution. Or Z in the temporal case. Thirdly, there's some variational structure. And fourthly, the equations satisfy there's some sort of prescribed asymptotic behavior at infinity. Okay, let me illustrate via a couple of examples. So, example one. Say, let's take a Hamiltonian system of ordinary differential equations. So Q double prime plus B sub Q of T and Q equals 0. And the potential V, say, is one periodic in time. So that will give you a Z symmetry for solutions. And let's assume that minus V is a double well potential. So minus V looks like, or maybe I should put, say, the origin at one of the wells. Here's 0 and, say, psi. So V minus V has minima at 0 and psi independently of T. Okay? And in that case, there's a corresponding functional I of Q equal the integral over R, say, of 1/2 Q dot squared minus E of T and Q. That's the integrated Lagrangian associated with our system. And now you can, say, look at the class of curves which is asymptotic as time tends to minus infinity to 0, as time tends to plus infinity to psi, minimize over that class, and you can show there exists a solution of the equation which is heteroclinic from 0 to psi. And similarly, there'll be solutions which are heteroclinic from psi to 0. So that's what I meant by the prescribed asymptotics in this case. Here's another example. Now I'll show off. So second example, let's say take a PDE example. Let's look for solutions of this equation which belong to W12 or N. So they'll tend to zero. Those are the prescribed asymptotics in this case. So here's a corresponding. Oh, let's assume that A is one periodic in the components of X, in each of the components of X. The corresponding functional, so A is also positive. Okay. So the corresponding functional would be, say, 1/2 the gradient of U squared plus A U squared minus U to the P plus 1 over P plus 1. Okay, so this is a functional which near the origin looks like this. And here P is bigger than 1, I should have said. And the power will be less than the Sobolev cutoff point. So this will be well defined on W12. And along each ray, as you approach infinity, since P plus 1 is bigger than 2, this term will dominate at infinity. And so along each ray, look like this. So this is the sort of picture you associate with the mountain pass theorem. You have the origin is a local minimum, but it's not a global minimum. And so if the hypotheses of that theorem were satisfied, there would exist a critical point. Unfortunately, the hypotheses aren't satisfied here, but nevertheless, you can use kind of mountain pass argument to show there exists a positive solution of this equation, and so it'll look something like this. So-called one-bump solution. Because of the periodicity, you can always shift this, and you'll get the whole family, a Zn family of such one-bump solutions. Okay. Another common feature of such problems is once you have a basic solution, the one-bump solution here, or the solution that went from 0 to psi in my first example, you can try to construct more complex solutions by, in a sense, gluing together such solutions. So if you have a solution like this, and if you looked at a large shift of it, then, of course, the sum of these two functions is not a solution of the equation, but you can look for a solution which is near this, in the language of dynamical systems, which shadows this. And indeed, you can show, under some additional conditions, that there exist such solutions. In this case, you can find an infinite number of two-bump solutions, of three-bump solutions, and so forth. In the setting of the Hamiltonian systems example, you can find solutions which start off at time minus infinity, approach psi, stay nearby for a long time, and then asymptote to 0 again. So they go back and forth from 0 to psi. That would correspond to a two-bump solution here. That's a homoclinic solution of the equation. And you can look for solutions which have a greater number of such oscillations. Okay. Now the question, now finally to hybrid solutions, one can ask, well, the way one gets these complex solutions is, in this example, in a sense, we glue together two solutions which are minimax solutions, mountain pass solutions of this equation. Here, we glue together solutions which are minima. So, in problems where both minima and mountain pass solutions can coexist, can we glue together solutions of different types? Can we glue a mountain pass solution to a minimum, and so forth? Can we construct more complex solutions in that setting? So, and that's what I want to show you that you can do in a model case. And this is joint work with my colleague Sergei Molotin. So the model case we're going to look at is the following. So this is a PDE on Rn, and the function f will be assumed to satisfy, I'll call it condition f. F is C2 from n plus 1 into R. So by this I mean, well, x lives in Rn and u is a scalar variable, and f is assumed to be, say, one periodic in each of its arguments. In the simplest case, where n is equal to 1, this would just be some sort of nonlinear pendulum, okay, some sort of forced pendulum. Okay. Now, this problem has been studied by this equation has been studied by various people. As far as I know, the study of this was initiated by Moser in the late 80s. And it was furthered by Victor Bongert. And most recently by Ed Rabinowitz and myself. So actually, Moser and Bongert looked at a much more general system, much more general equation, which was quasi-linear. This is the simplest example of what they looked at, which retains the essential features.
What do you want of the solution? Periodic or something?
I'll come to that in a while. So, let me tell you some known facts about this equation. That's your question. So, and I'll go back to the low-tech thing.
Stop it anywhere?
Okay, so was shown by Moser, again, much more generally. So some facts. So first of all, there exist periodic solutions to this equation, say one periodic solution. Periodic in x1 through xn. And that's easy to obtain, namely, just look at the, again, the Lagrangian associated with this, L of u equal 1/2 gradient of u squared plus f of x and u. And we'll look at the integral over Pn of L of u. So, and let's simply, let's call this I of u. And now let's minimize I. over W12 of Tn. Minimize this over the class of 1 periodic functions. And it's not difficult to show there exist minimizers, there are 1 periodic solutions of this equation.
Is f positive then?
Here, no.
And it's minimized?
So it doesn't, well, of course, in a sense, f is only determined up to a constant. You can make it positive if you wanted to. But just minimize, and there will exist minimizers. Each minimizer is a 1 periodic solution of this equation. So minimize this. So let's call the set of minimizers, say, M0, the set of U in W12, Tn, such that I of U equal C0 equal N. Okay. And second fact, shown by Moser, the set of minimizers is an ordered set. A little bit surprising. This again is very elementary. It uses the variational nature of the problem together with the maximum principle in a clever way. I don't have enough time to show you the details. And by ordered, I just mean if, say V0, W0 belong to M0 implies that V0 is less than W0, or V0 is greater than W0, or V0 is identical to W0. And indeed, whenever U belongs to M0, so does U plus 1. Now, since this is an ordered set of solutions, then let's look at the graphs of the members of this set. So, as I said, whenever you have 1, you're going to have lots. Now, either Rn plus 1 is filled by the graphs of these solutions, or there are going to be gaps somewhere. There'll be some points in Rn plus 1 which don't, and then there'll be a smallest solution above it, that point, and a biggest solution below it.
Is it obvious that there's more than one solution?
Sure. Whenever U is a minimizer, U plus 1 will be a minimizer because of the periodicity in U. Okay, so U in M0 implies U plus K in M0 for all K in C. By the way, I should have mentioned that Spreadlinski and I got into this not by looking at this problem, but looking at some Allen-Kahn models of phase transitions. And there, F is very different. F was like a bit like the Hamiltonian case before. F corresponds to a double well potential, which looks very different from a periodic F here. But if you take such a periodic potential, restrict to looking at the region between the pair of minima, and redefine it to be periodic outside that region, then you fall into this class. And if you can show that a solution lies between this pair of minima, then it's a solution of the original equation. And indeed you can. Okay, so that's what led us to this. Okay, so fact 2. Fact 3. Well, let's suppose that we have such a gap. Let's suppose we have some V0 and W0. In the Allen-Kahn model, it would just be the region between here and here would be a gap, corresponding gap. Okay, and it's in some sense these, well, one can show in a precise sense that gaps are generic. But let's suppose we have such a gap. We'll call V0 and W0 a gap pair. And then it was shown by Bongert that that whenever you have such a gap pair, there exists a solution of our equation which is heteroclinic in x1 from V0 to W0. So as a function of x1, it's asymptotic to V0 as x1 tends to minus infinity, to W0 as x1 tends to infinity, and it will be periodic in the remaining variables. Okay. And likewise, there'll be heteroclinics like this. Now, the way you'd think you might get them is to say, let's look at the integrated Lagrangian again. Now, over the class of functions that looks like this, with these properties, and now we'll look at it on R cross Tn minus 1 and minimize. But now we'll get into trouble, because suppose, for example, f were positive. Then for every admissible function, the integral would be infinite. So in order to have a sensible variational problem, you can't deal with this function. You're going to have to modify things in some way. You're going to have to, what Skrzydlewski and I call, renormalize the function. Okay. And the way you renormalize, or a way to renormalize, is as follows. Let's take R cross Tn minus 1 and let's break it up into unit pieces. So if we go from I to I plus 1, let's call that T sub I. Okay. And what we're going to replace this functional by is, say, the sum, let's call it J of U, equal the sum of the integral over Ti of L of U, and we'll renormalize by subtracting off C naught, this min over the class of periodics. And it turns out this functional has some nice properties. It's going to be bounded from below on the class of functions that looks like that, and it's going to have some nice compactness problems. You can now minimize this over a more precisely defined class of functions and show there exists a minimizer to that variational problem, which will give you the heteroclinic solution here. And likewise, you can find heteroclinic solutions like that. Okay, so there exists heteroclinics, minimizers. And it turns out again that the set of such heteroclinic minimizers is an ordered set. It's even the same sort of argument that is, the ones of this type are ordered, the ones of the other type are ordered. In fact, whenever you have one of these, say u of x, then u of x plus e1, unit vector in the x direction, is also going to be a minimizer of the same type. So there'll be lots of those. This again is sort of the symmetries that I indicated before. Now, either the set of minimizers is going to totally fill in the region between the gap pair, the degenerate case, or there'll be gaps between such minimizers. So let's suppose we have a gap pair. So suppose that B and W is a gap pair. Okay, and then it was shown by Bolletine and myself a while ago that whenever you have such a gap pair, in fact, there's a mountain pass solution in between them. Okay. If you think of the functional, if you look at J of U, J takes on the same value at V and W. So when I think of a graph, so here's a pair of local minima. So shouldn't there be a mountain pass solution somewhere via the mountain pass theorem if it applied? Unfortunately, it doesn't apply directly, at least. But it turns out there is a mountain pass solution, and in between these two.
What does a gap pair mean? I thought there were no solutions between.
A gap pair means that there are no other minimizers between them. Okay. So in the set of minimizers, there's a gap. But now we find a mountain pass solution that actually lies in between these two guys. Okay. So now we have a situation where minima and mountain pass solutions coexist. Can we glue such solutions together? So say here's a mountain pass, here's a minimizer of this type. Can we find a solution that looks like that? It's a homoclinic solution by gluing together these two. And so I want to show you how to do that, or at least in this setting. I should maybe also mention at this point, you can ask, can you glue together minima here? Forget about the mountain pass solutions. And that was studied by Rabinowitz and myself. We can glue minimizers. So you can find solutions that look, for example, like this as a function of x1 and are periodic in x2 through xn. And you can also have solutions that glue them to yet another one. There are an infinite number of solutions which undergo two transitions. There are an infinite number of solutions which undergo an arbitrary number of transitions between V naught and W naught. Okay. Moreover, let me say it this way. If you look, let's say we take our gap pair VW here, and let's let tau K W equal W of x minus K E1. So we shift W over K units to the right. Then for each large K, there'll be a solution in some sense corresponding to V and well, I'm sorry, I shouldn't have said it that way. Suppose, let me backtrack. Suppose I call this V plus and W plus, and suppose I have a corresponding W plus and V plus, and W minus and V minus. Suppose I have a pair of gap pairs, one of this type and one of this type. And here I'm thinking of W minus. Then you can find a two-transition solution which, say, approaches, as k tends to infinity, will approach, say, v plus from the bottom, from below, and approach w minus shifted from below, as k tends to infinity. Okay, so given these facts, how do we construct a hybrid solution? Now I know two ways to do it. One is a bit more elliptic in nature, one is a bit more parabolic in nature. It's always good to have two proofs of something, because remember the old story about somebody who gave a talk, he stated his main result, and somebody in the audience said, I have a counterexample to your theorem. And the speaker said, that's okay, I have two proofs. Okay. So anybody has a counterexample? So the idea is as follows. I'm going to start off with this result about the existence of minimizing the existence of such homoclinic solutions. These homoclinics, by the way, these multi-transition solutions are not minimizers. They turn out to be local minimizers of the functional j. You have to put some further constraints on the class of admissible functions, and therefore that makes them local minimizers rather than global minimizers in the sense of these heteroclinic solutions. So let's start off with such a solution. Cheating a little bit. And as k, this will depend on some parameter k, which sort of measures how much we're shifting, one of our basic solutions. And this is, as we let the parameter k tend to infinity, this is going to approach, say, some, this is a b plus, and here's a corresponding w plus. And here's tau k w minus. So these go up. Infinity. Oops. This approaches the tau k w minus. So let's call this, say, dk. So dk is a two-transition homoclinic solution. Here's a gap pair of minimizing heteroclinics, and here's another minimizing heteroclinic. And let's look at the region between vk and wk, w plus. And now associated with our PDE, which I have erased, is a corresponding heat equation. And let's make an observation that look at the shaded region. Let's call it maybe the shaded region RK. So RK will be invariant under the corresponding heat flow. That is, if you take initial data above VK, above this homoclinic solution, you're going to stay above it. You're not going to be able to cross it. And the same thing is true here. If you start below W plus, you're going to stay below W plus. If you start below tau k W minus, you're going to stay below it. So that involves a simple comparison argument. So Rk is invariant for the heat flow. That is for the solution of that equation. Any data in there stays in there. It'll exist for all time. Secondly, if you look at the functional, let's look at J of U. Let's say we take initial data. Is say U, we'll call phi of t U is the solution with initial data U to the parabolic equation. Secondly, so let's look at J of phi t U, and let's take its derivative. And if you make a little calculation using the fact that phi is a solution of the equation, you'll find this is equal to the integral of minus this would be phi where we're integrating over r cross Tn minus 1. So the J evaluated on the solution has a derivative which is less than or equal to 0. In other words, J is a Lyapunov functional for the heat flow. It's also not too difficult to show that that the J is bounded from below. So let's look at any U any function U in there, lying above dk and below the smaller of W plus and tau k W minus. Then if U belongs to Rk, then J is bounded from below. Okay, so that's not difficult to show again. And now we can use a kind of mountain pass argument with heat flow replacing the usual sort of negative gradient flow that you apply for mountain pass settings. So let's define a class of functions. Say h sub k is the set of h which are continuous from 0, 1 into Rk. So for each theta in 0, 1, we have a function which lies in there such that h of 0 is bk, h of 1 is the min of W plus tau k W minus. So we take a homotopy of functions which start off at bk and wind up at the upper end of our region. And now let's define bk equal the inf max of j of h of theta for theta in 0, 1. So for any such curve, for any such homotopy, we'll evaluate J along that homotopy. We take the largest value J and then take the inf over H in HK. That's sort of a mountain pass setting. And then theorem, dk is a critical value of J. That is, there's some solution of our equation corresponding whose value, which when we evaluate J at it gives you dk, and dk tends to, well, the mountain pass critical value, the one I mentioned over here. So suppose we have, this is some, let's call it U plus, say J of U plus is equal to B plus, which will be bigger than C plus equal J of B plus equal J of W plus. That's the minimization value here. Here's B plus is the mountain pass value. And we'll have a corresponding C minus with the minuses here. So this tends to B plus plus C minus. So the sum of the mountain pass value plus the minimum value. So as we're spreading apart, in some sense we're tending to a mountain pass minimizer, a mountain pass critical point, the one of the ones we get there, plus one of the minimizers we get for the minus problem. Okay. So now you'd also like to say that the solution we get here, can I give that a name yet? So let's call this there's a critical value. Suppose the corresponding point, say dk equal J of UK. So we'd also like to show that UK tends, in some sense, to one of our mountain pass critical points plus one of our minimizers in some limit sense. And one can do that. The UK, or the shift tau k UK minus tau k W minus will convert to 0 in a sense, but it's harder to get. This we haven't really settled properly. That the UK itself should converge to U plus, say, to a mountain pass critical point of the original problem, because there's a certain lack of a Palais-Smale condition which would allow you to control that. Okay. Well, I don't really have enough time to go into the details of the argument. Let me just make a few other remarks. As I said, we're going to use the heat flow to basically take any h such that the max of J of h is close to dk, and show that if you turn on the heat flow, that as time tends to infinity, it's going to converge to an actual critical point which is close to dk. And since you can start out as close to dk as you like, by taking a sequence, you'll get a critical point corresponding to dk. So it's a mountain pass type of argument using the heat flow. Now, this sort of argument gives you, glues a mountain pass to a minimizer. The same sort of argument can be used to glue any number of minimizers to a mountain pass solution. suppose you wanted to glue two mountain pass solutions. Well, you can use the same sort of idea to construct an invariant region. So the natural thing to do would be, say, if we wanted a pair of mountain passes, so say let's say take a gap pair here again, and then appropriate shifts of these. Of tau k w of v minus and tau k w minus, and corresponding to a solution like this again, we'll have, well, the same decay even. And now we'll need, well, and now you can take, well, you can take now the min of W plus and tau k w, I'm sorry. We have to replace vk by some vk bar so that we go below tau k v minus rather than tau k w minus this time. We have something a little smaller. And so upper region will be like this. So now we're getting a fatter region on each side. Before we had a skinny region to the right, which is a W minus rather than a V minus. So now we'll have a fat region on each side, in a sense. And so we'd like to glue together a mountain pass solution here and a mountain pass solution here. And you have to use it doesn't suffice to work with a class like HK. You have to work with a more complex class. You have to work with something like H continuous from 0, 1 squared into the new RK. And we need something about the behavior of H on the boundary of this set versus the behavior of H inside. You have to have some sort of appropriate non-trivial topology. You have to exploit that. I don't want to, I don't have enough time to make that a little more precise, but you're going to have to exploit the non-contractibility of something to get an appropriate class of sets with respect to which we minimize. So if you wanted more mountain passes, then you'd have to reflect it in here. You'd have more copies of 0, 1 to an appropriate power. Okay, I think I've run out of time. Thank you.